In this video, we are going to be solving partial fractions. So, using the previous knowledge from the last video, we are going to set up the problem, and the problem is going to be 1 over x squared plus 3x plus 2. So when we set this up, we factor the denominator and we get x plus 1 and x plus 2. So for the first partial fraction, we'll put in a constant, over x plus 1, plus another constant, b, over x plus 2. Okay, so now to solve the partial fractions, we multiply the entire thing, the left side and right side, by the least common denominator, which is x plus 1 and x plus 2. And when we do that, we multiply the we multiply the left side first, and we get that the bottoms cancel out, the denominator cancels out, and we get 1. And then we do the second partial fraction, and we get a times x plus 2 plus the third partial fraction, and we get b times x plus 1. Since the x plus 2 and x plus 2 cancel out, and the x plus 1 for the first partial fraction cancels out with the x plus 1. So now what we can do is we can multiply out all of this, and we get ax plus 2a plus bx plus b. So now we need to group like terms before we set up linear equations to solve for a and b, and we get ax plus bx plus 2a plus b. And now we could take out an x, and it'll equal a plus b plus 2a plus b. So there's no like term with the x on the the left-hand side. So what we do is we set a plus b equal to 0, and now we can set 2a plus b equal to 1, since the 1's a like term with 2a plus b. So when we solve this, we need to cancel out one of the terms to find out the other one, a or b. So we can multiply the top by -1, that way the b's can cancel out when you add them together, and we will get -a plus -b equals 0, and the bottom stays the same, 2a plus b equals 1. And then when we add these together, the b's cancel out, and we get a equals 1. So now that we have a equals 1, we can plug the 1 in for one of these equations and solve for b. So if we plug it into the first one, we get, one of these equations we'll plug it back into. So let's do the first one. So we have we have 1, positive 1, plus b equals 0. So now, because we're solving for b, we're going to subtract -1 from each side, and we get b equals -1. So now that we have what a and b equals, we can plug it back into our original fractions. So we get 1 over x squared plus 3x plus 2 equals, so we plug in 1 for a, 1 over x plus 1 plus, now we have -1 for b, so we can put -1 up here in the numerator and put x plus 2 in the denominator. And that is the answer. Alright, so that was a distinct linear factor problem, and now we are going to try a different one. We're going to try to move on to a different one. So we are going to do an irreducible quadratic problem. So when you're doing an irreducible quadratic problem, you're going to set it up a little bit differently than the distinct linear, but you're going to use the same steps to solve for your constants. So for this problem, we're going to do minus 1, x squared minus 1 all over x times x squared plus 1. And then we are going to set it up with an a over x plus a bx plus c over x squared plus 1. Alright, so like we did before, we are going to multiply both sides by the least common denominator, which we have as x times x squared plus 1. And when we do that for the left-hand side, multiply to the left-hand side, and the denominator cancels out. So we get x squared minus 1. And now we're going to do it for the first partial fraction. And we get a, whoops, a little too high. We get a times x squared plus 1. And then if we do it for the second one, second partial fraction, we get bx plus c times x squared. Oh, I'm sorry. That cancels out. So when we do it, the x squared plus 1 cancels out. And we will actually just get an x. Alright, so now we're going to multiply it all out. We still get x squared minus 1 equals ax squared plus a plus bx squared plus cx. So we're going to do the same thing as the last problem. We're going to group like terms. And we get, if you take out an x squared, you get a plus b. Because that would equal, if you multiply it out, ax squared plus bx squared. Plus c of x, there's no other like term, plus a. Okay, so now we're going to set it up into linear equations. And to do this, oh, we don't have enough room there. We are going to write it like this. So there's a term over here that's an x squared, and there's a term over here with the x squared. So you can write it as a plus b equals 1, because there's a 1 in front of the x squared. And then there's no degree 1 over here for x, so we just set c equal to 0. And now the a we set equal to negative 1 for the third linear equation. So we get a equals negative 1. So now we already have two of our constants. We have a equals negative 1 and c equals 0. So this is a little bit easier than the last one because we can plug negative 1 into our first linear equation to get what b is. So when we do this, we get negative 1 plus b equals 1. And when you add 1 to both sides, you get b equals 2. Alright, so we have our c, our a, and our b. And now what we do, just like the last one, we plug it back into the original partial fractions. And we get sorry, ran out of room. I'm going to move it over here a little bit. We get x squared minus 1 over x times x squared plus 1 equals, and then we put a equaled negative 1. Let's check. Yeah, a equals negative 1. So we put negative 1 over x, and then plus, we got 2 for b, so we go 2x, and c was 0, so we don't have to put a plus 0 because it means the same thing. So we put 2x over x squared plus 1. Alright, so this is our final answer. That's what happens when you plug the a, b, and c back into the partial fractions. Okay. So now we're going to move on and we're going to do one with a linear, a repeated linear, but we're going to also do an irreducible quadratic that's repeated. So combine everything a little bit, and we get, so we're going to do this problem. We're going to do 2x squared plus x plus 8 all over x squared plus 4, which is an irreducible quadratic, squared, which is repeated. Okay, so to set this up, we are going to set it equal to ax plus b over the first term, x squared plus 4, since we need one partial fraction for each squared. And then it'll be plus cx plus d over x squared plus 4 squared. Okay, so just like before, we are going to multiply the left and right side by the least common denominator, which we get x squared plus 4 squared. So if you do it to the left-hand side, they cancel out, the denominator cancels out, and we get 2x squared plus x plus 8 equal to, we get ax plus b times x squared plus 4 plus, and then this denominator cancels out, so all we get is cx plus d. Alright, so we're going to FOIL ax plus b out with x squared plus 4, and we're going to get 8. So we're going to get ax cubed plus 4ax plus bx squared plus 4b. And then we carry everything down, so we get plus cx plus d. So there's nothing we can combine, but we can write it a little bit differently so it's correct. It would be ax cubed plus bx squared plus 4ax plus 4b. Oh, sorry, my bad. It's actually, you can combine a few things. So we have an ax cubed plus 4ax plus cx plus bx squared plus 4b plus d. And this all equals 2x squared plus x plus 8. Oh. Okay, so we're going to do some linear equations again. There's nothing that's equal on the left side to x cubed, nothing else that's an x cubed, so we set a equal to 0 in our first linear equation, a equals 0. And then we go to the bx squared, and we get b equals 2, because there's a 2x squared on this side. And then we can do 4a plus c equals 1, because there's an x. And then lastly, we can do 4b plus d. Okay, and that equals 8. Alright, so we already have a couple of the constants. We have a equals 0 and b equals 2, and we don't have to do anything else for those. So we can plug in a equals 0 for the third linear equation, and if we do that, we will get so 4 times 0, so it would be 4, 0, which would be 0, plus c equals 1. And since these cancel out, we get c equals 1. And now we can plug in 2 for b. So we get 4 times 2 plus d. You can see where I got that. I got the b equals 2, and I just plugged it into this last linear equation. So 4 times 2 plus d equals 8. So it'll end up being that d equals 0, because you'll want to subtract 8 from both sides. So you get d equals 0. And we have all of our constants. We have a equals 0. Whoops, sorry. And b equals 2. So now we just want to do the same thing, and we want to plug back these numbers into the original equation. So, whoops, we're going to do it over here, and we get 2x squared plus x plus 8 all over x squared plus 4 squared equals, so first partial fraction had x squared plus 4 on the bottom. The other one had x squared plus 4 squared as the denominator for the second partial fraction. So let's see what we got. We got that a equals 0 and b equals 2. So we're going to plug those in for the first one. So since a equals 0, it would be 0 times x, which we don't do anything for that because we'd plug in the 0 for x, and anything times 0 is 0. So for b, we could plug in, what did I just say? 2? Yeah, 2 for the numerator. And then for cx plus d, cx, we got 1 for c, and d equals 0. So we can put an x because c equaled 1. And then d equaled 0, so we don't have to write anything for that one. So this is the answer. So that's a little bit on how you solve partial fractions.